at first I'd like to appreciate the organizer to give me a chance to talk at this workshop. And also it is a good chance to visit Paris. So it is a second time. So I visit Paris is 20 years ago. At that time I stayed at the University of Copenhagen as an assistant professor and under the Georg Pedersen to study the non-commutative dimension of C-star algebra. So before operator algebra, I construct the sequence of indecomposable positive maps on any n by n matrix. So that was constructed around 1990. But at that time, I didn't know the quantum entanglement anyway. Just I construct such an indecomposable positive maps on matrix algebra just comes from the mathematical interest. But after that, around 2000, several times I got an email from physicists and they asked me about the quantum entanglement. Then, and I understand that, it seems like my positive linear maps is related to the quantum entanglement and also sometimes useful or candidate to detect is the quantum entanglement. So after that, almost finished the joint program with Chris Phillips about treasure Hornets action on C-star algebra. So I started to study the quantum information theory. So this is in some sense simple CV. Then today I explain about in some sense a simple application of operator theory to the entropy. This morning session, Professor Hiai present such an entropy using the, in some sense, is that the Tomita-Takisaki modular theory. But in my case, it's a very simple one, so everybody can understand easily. Okay, here at first, this is the usual thing is the definition of positivity on Hilbert space. I use a notation is A is positive, is also like this one, and also BOH double prime means that positive invertible operators on H. Then here is an important function is that the operator monotone function. So definition is easy. So give any positive operators. So like this one, so F keeps the orders. So we call operator monotone functions. So typical example is Ts power, but S belongs to 0, 1. Or F of T is logarithm T. This is a typical example of operator monotone functions. Similarly, there is an operator convex. This one is already discussed in the morning session, but this is a definition of operator convexity as usual. And the typical example is a Ts power, but in this case, the range of S is -1, 0, union, and 1 and 2. Okay? Or this is a typical. This is related to the information theory, as you know. Also, if H is n-dimensional, in this case, we can define the operator n monotone or something. N monotone is weaker than operator monotone function. If you like calculus, so this is a P1. This is a 1 monotone, 2 monotone. So I is an interval of somehow, and etc. decreasing, and also here is operator monotone like this one. But in this case, operator monotone is fortunately is the intersection of P of n, I. So each inclusion is this is a restrict proper inclusion. So we know now how to construct the example. So, for example, it's a Hansen G. Tomiyama. They present some algorithm related to operator convex, and also myself and Silvestrov and Tomiyama is this is a gives an algorithm to make a n-monotonicity. So important of operator monotone function is that this is just a peak function. What is peak function? This is so famous one. So if you consider this plane, upper plane, then analytic function is called a peak function. So satisfy this one. So fortunately, peak function has a representation theory like this one. So beautiful. This is beautiful result anyway. Then example is like this is z power and also logarithm. And the important result is by Leuna in 1934 is for any operator monotone is a peak functions. That's why any operator monotone has a representation theory, representation form. In particular, if f is a non-negative function on 0 infinity, then f can has this type form. So sometimes people use this representation form to calculate something. But in my case is I don't like to use this representation theory because I would like the extended version of n-monotonicity. Here, so they don't have such a representation theory. That's why. So usually I don't use this representation form to get something. But sometimes I need this one. This is a typical example of operator concavity. And to prove this one is usually not so easy. There is several criterion to how to prove the operator concave. But fortunately, Furuta, he gives a very simple proof not using criterion. So just shows a directory. So proof is very beautiful and simple and only 1 page or 2 page. So another important result is this operator monotone function. Class of operator monotone function is a correspondence to the operator mean. So that is appeared in the title of my talk. So that was done by Kubando. And here is a definition of, at first is operator connection. Operator connection is that some binary operation on possibility operators satisfy 3 conditions. First condition is in some sense monotonicity. Second is also how do I say? But this type of inequality. This type of inequality is very useful. And also, third is decreasing property. So this one is a strict topology. So Bn down to B and then down to A, then An sigma Bn down to A sigma B. So this one is also sometimes useful. If you use this third condition, so we know that both A and B is invertible positive operators. So we can assume that invertibility. So operator mean, okay, this is a definition of connection, but operator mean is that just plus connection and also satisfy this condition 1 sigma 1 equal 1. This is in this case sigma is called operator mean. So important thing is that there is a correspondence between the operator monotone and operator mean. So correspondence is very easy. Given an operator connection, then you can easily construct operator monotone like this one. F sigma of t equal 1 sigma t1. Conversely, if f is given, operator monotone is given, then you can construct this operator connection like this one. So this form is very important. Because maybe if someone studies entropy, then many cases you can see such a form in the or in the entropy. That's why to calculate the entropy or to get the upper band and the lower band, so we can apply the operator mean. That is my idea. Okay, this is very important. So many times appears. Here is an example. This is when is a left hand. This is the left hand side trivial cases. So correspondence to operator monotone function is just a constant identity. Right hand side is just a t. Okay, I don't know how to say, but this one is correspondence to this one. This one is a harmonic mean. We call this is correspondence function is like this one. And this is also famous one, geometric mean. This one correspondence is a root. The last one is arithmetic mean. So this one corresponds to this one. So usually, my interest, one of my interests is to classify the operator mean by using the operator inequality. So if I write this is a world of operator connection. Then here is a I usually I would like this one. This is a operator mean. This is operator mean. Here, center is like this one, and here is a arithmetic mean. Here is a harmonic mean, and so center of harmonic mean and arithmetic mean is there sharp. Here is one is one minus t e 1. Here is omega 1, and this is right. So there is path like this one. So we can parameterize is operator mean. So starting here and starting, so this is a weighted geometrical mean, and then for each t, so there is a weighted arithmetic mean and weighted harmonic mean. For example, this one is correspondence to like this one, t of like this one. By using operator inequality, but this time is that how to apply the operator mean to the quantum entropy. Okay. Then this is okay. Operator monotone is also stable, like transpose or adjoint, and also dual. Then we call symmetry if f equal f prime, and self-adjoint f equal f star. Then, this is a simple calculation. So if it's a symmetry, that means that f equal f prime. In this case, and also f1 of 1 in between the harmonic mean and here. Okay. So usually, symmetry is correspondence. This one. So we can define the symmetry and the self-adjoint in operator mean as similarly, and this is a weighted version. Weighted version is that if derivative of 1 equal lambda. In this case is so okay, here is a lambda case is in this case is so operator mean is exists is this interval. This is not so difficult. A little needed argument, but so not so difficult. Okay, anyway. So similarly we define the transpose and also adjoint and dual and also define the symmetry and self-adjoint. So both of the cases is the same. So because so the world of the operator monotone is a correspondence to the world of operator mean. So if you that is dependent on you. So if you like operator monotone function, then they so use operator function. But if you like to the operator mean, then so you study the from the point of the operator mean. So interesting is that so this one is symmetry, and this one is symmetry, and also this one is a self-adjoint. But the only self-adjoint this line is only sharp. Okay, there are many symmetry, but also there are many unsymmetry. So interesting is that any two symmetry, there is exists a non-symmetry, like a rational and irrational relation, rational and irrational numbers. That's why, so in some sense, very interesting. So, but this is just a mathematical side, not a quantum information theory. But so anyway, so that is the world of operator mean. So this is a picture which I have in mind. Usually, so here is a Kubando correspondence theorem, and also Pets is also shows that the correspondence, there is a correspondence, the set of operator mean and the set of monotone matrix. Monotone matrix is related to the matrix on density matrix or so this one is applied for the geometry of density matrix. That's a quantum information geometry. And that's why, so this one is contained quantum information theory. This time, it's, I don't so explain about this monotone metric. I just application of operator mean to the quantum information theory this time. Okay, here is at first. This is also standard answer. But anyway, I'm in some sense beginner in quantum information theory. So entropy is how much uncertainty there is in the state of a physical system. So it is a crucial concept in quantum information theory. This is a famous Uhlmann entropy. Yeah, maybe you know. And so next is so relative entropy, or we sometimes people call Umegaki entropy. So this is the relative entropy definition is like this one. So this relative entropy has so basic property is 5 basic property: non-negativity, unitary invariance, additivity, joint convexity, and preserve completely positive map. And this is a monotonicity people call. So usually, so when people defines a new entropy, at that time, so people try to check usually non-negativity and also joint convexity and monotonicity. So those 3 conditions usually people try to check is it that is true or not. And there is upper bound about so Umegaki entropy. This is done by Hiai-Pets, 91, and later so Furuta gives another approach. This one is less than or equal to this value, and this one is also less than or equal to this value. So here, it seems like operator mean here, but logarithm is not a non-negative positive function. That's why, so this is not an operator mean, but a similar operator mean. And also, so Berkin and Stainsky is very difficult. And also Fuji and Kame is introduced, so this type of operator entropy. And this S of H is a space ratio, and also this H is defined like this one, and for satisfy these conditions. So logarithm is not a non-negative operator monotone, but so Fuji and W Fuji, Junichi Fuji and Masatoshi Fuji, and Seo calls the map sigma F. So like this one is solidary. In some sense, extension version of operator mean. And they study the basic property of solidarities, 19. But unfortunately, so their paper is published in some journal. It is not so easy to get it. So that are so serious problems. So anyway, so there is a upper bound. So next is operator entropy. So Nakamura and Umegaki studies operator entropy like this one. So they concentrate to prove the operator concavity of function in this one. At that time, it's very difficult, convexity. The Furuta succeeded to give simple proof in 2000, as I said before. Then, so Fuji and Kame introduced a relative operator entropy like this one. Okay, if B is identity, this is correspondence to the polynomial entropy, and if A equal identity, so we get the SI A is logarithm A. So this one is very important. So and also Uhlmann extended the Umegaki entropy using the quadratic interpolation, and later so Fuji and Kame considers a path from A to B. So here is a path from A to B, and so they consider the weighted geometry like this one. This is a definition of weighted geometry. So if you consider this one, the limitation of this one, then you can get this this is a Umegaki relative entropy, and also this one is minus S of B of A. A. That's why this form is very important. And also, it's difficult pronunciation. Port and Ray. So discuss the geometry of the geodesic by the path of operator mean in the space of possible operators. This is 1903. It's okay.
The second one would be minus B, the limit is t goes to 1.
Minus.
Sharp t b minus b over t.
Yeah. No. This I think this one is correct. So this one goes to the 1 and 1. 1 is 1. 1 is a cancel is b minus a. So and the logarithm b minus a. That's why it's okay. Yeah. Okay, next is also double parameterized. So if you consider like a double parameterized version, in this case, is if S is minus 1, is you can get weighted harmonic mean. And if S equals 0 is the weighted geometric mean. And one case is weighted arithmetic mean. The next is very important. If t is goes to 0, so we can get this one. So this one is called the Tsallis entropy, Tsallis operator entropy. Tsallis relative operator entropy. So this one studies Reny, Furuichi, 2005. but so according to Fuji Kamei, they already considered such a entropy in 1809. But this is just a history, so I don't know. Yeah, maybe true. And I don't know. So they know so their result or not, because the problem is that their paper is not was not published in the major paper. That is a serious problem. So it's not so easy to get a copy of their papers. Here is so maybe a so famous Tsallis entropy. So Tsallis entropy torrential version. This is Tsallis entropy. In this case, this one is this type so map, and so this one is if s is goes to 0, this goes to logarithm of x. That's why so Tsallis entropy is very important. Then here is some result by Furuichi, Reny, Kuriyama, and also Furuta. Given a possible operator and satisfy two conditions, and also H is like this one. So then, so we can get upper bound on Tsallis entropy like this one. Okay, if U goes to S, it goes to 0. Then, so this Tsallis entropy goes to Umegaki entropy or Liat-Quantum entropy, and also, so we already so previous. I already explained about this inequality. Okay. So Furuta so gives us such a so upper bound, and this one is a generalized. He called a generalized control which constant. So so maybe someone interested. So this one is very complicated for me. Hs minus h is 1 h minus 1 times 2 ss minus 1 hs minus hs minus 1 and this. So this value is computable if given matrix such a matrix, two positive matrix, positive semi-definite matrix or positive matrix. Then so we can compute this value. And also Furuichi so gives another so upper bound is like so this one. Tsallis relative entropy is less than or equal to s, so torrential of n minus b plus over s. So this is a definition. This is a standard notation, maybe. Okay. So this proof is in some sense easy because this comes from the famous inequality, generalized Powers-Stammer inequality, which was done by Ordinant and another person. So this one. Just using this inequality, so you can get this one easy. Okay. And when I found this inequality, so I thought that we can extend this inequality more general operator monotone function, because S power means that Ts power. So Ts power is an operator monotone function. And in fact, so we can extend it like this one. Let f be an operator monotone function on 0 infinity is satisfy this one. Then for positive inverted operators, so we can get this inequality. This is an extended version of ordinand. This is generalized Powers-Stammer inequality. This inequality is so used for the quantum hypotesting theory. That's why we believe that this inequality is also quantum hypotesting theory. But I don't know. So anyway, so Furuichi, so after present Furuichi two upper bounds for Tsallis entropy, so he gave us a question like this one. This inequality is true or not? Okay, this is the two upper bound for the Tsallis entropy. So he checks this one is true or not. But this one is a correspondence to just a modified easy, just a simple calculation. You can get this is equivalent to inequality. Then you can find some operator mean paired. So this is arithmetic mean. So that's why operator inequality version is like this one. Okay. So problem is that this operator inequality is holds in general or not. But Furuichi shows that this is wrong. So that's why I try to consider when this inequality holds. Okay. So to consider to solve this inequality, from some mathematical point, this is related. I found that this is related to reverse Cauchy inequality. So this one is a number usual commutative case. So people call reverse Cauchy inequality. Then when n equal 2 case is this one is related to the ordinate inequality. Okay. And I already this one explain about it. And before Furuichi explain about the Furuichi inequality. I give the proof of this one. No, not proof. Sorry. So Furuichi is gives this inequality is not true. So then I consider that n equal to and also s. So he considers weighted geometrical mean. So that's why I consider s equal 1/2 cases like this one. Then after that is we extended this version is a more general setting is sharp is replaced by any operator mean. Then we try to clear these situations. The answer is like this one. Yeah, this is answer. Give us strictly positive operator monotone function. Satisfy f of 1 and 1. This means that the correspondence operator connection is operator mean. Then any positive operator satisfy AB plus BA is positive. Then this inequality falls. Any operator mean. So proof is very simple. We don't use representation form. Just use a hand composition like this one. And then from the assumption, AB plus BA is positive. That's why we get this one bigger than this one. So just root considers a root, so you can get this one. So that means that A minus P is like here, is positive. Okay. Then next, A minus P equal B minus Q is less than or equal to B. That's why we have this inequality. Then F is operator monotone. That's why this is true. Then, that's why A sigma F A minus P. So this is a definition. But A minus P is less than or equal to B. That's why we can replace this one. F is operator monotone. So this one is correspondence this one. Okay. So we don't use a difficult argument, just a simple argument only. Then finally, A sigma FB, this is a definition, is less than or equal to this one, bigger than equal to this one, and A minus B is so less than A. That's why this inequality is hold. The fortunately, so A minus, so this, if both operator is the same, at that time this one is equal to A minus P, then what, so this is what? This is a target. So that's why we can so get the proof. So very simple. So conclusion is that so for any possible operator A and B with AB plus BA, in this case, Tsallis entropy is upper bound is like this one. So order is this one is smaller than this one. This is answer. Okay. But the problem is that so still we don't know the secret when the inequality is hold. So this condition is that AB plus BA is positive is that in some sense strong, not strong, but so not so easy to check it. And also here is a famous result. And so for any n, if this is positive, then AB and BA. So if so for any n, so A, B, n power plus B n is possible. In this case, it's A and B, and commutative is a usual, so classical one. So that's why, so AB plus BA, positivity of AB plus BA is, so in some sense, so near to the classical situations in some sense. But we, so explain, we clear the situation, so like this one, so Tsurumi is my student, so he stayed as IHP for maybe 3 months until the end of December, middle of December. So you may ask him about this theorem if you are interested in. So Wada is so professor, and when alpha is half, in this case is so this is a question by Furuichi. If this inequality is hold for any positive operator, so this means that this sigma is has a whole weighted arithmetic mean. This is the answer. That's why, so geometrical mean case, there should have a counterexample. This is the answer. So in some sense, this is a beautiful, I don't know, but this is a beautiful characterization of this inequality. And the next is that, so what is the range of beta? Next question, what is, okay, there exists beta, but how about, how many exist? So that is the answer like this one. Range is like this one. Beta is maximum like this one and this one. This is the answer. So anyway, so we are now understand that in some sense we can succeed to give so some answer to Furuichi's question. In particular, if sigma is a symmetry, symmetry means that A sigma B equal B sigma A. In this case, is only one. Only one. So that's why. So symmetry is usually symmetry means exists is this line. That's why only arithmetic mean this is a natural answer anyway. Yeah. So this is in some sense. So I believe that this is in some sense one application of operator mean to the quantum entropy. Okay. So next is that generalized operator entropy. So this is a new topic and the future problems of which I try. Okay, 2012, Furuichi introduced generalized Tsallis entropy, okay, like this one. Psi is not necessarily operator monotone function, just strictly monotone functions. And P1 and Pn and R1 and Rn, this is a probability distributions. So they just a commutative case. So he defined the ds psi entropy is like this one. So this is invertible. So invertible in some sense difficult part is how to control. But if so, you put the psi is so this map. Then so this is cancel. Then so this entropy is a Tsallis entropy. Okay. And also, okay, here you can replace by using the so trace form and the diagonal matrix and the P and the diagonal matrix R. That's why you can generalize this entropy for quantum case like this one. Okay, this is so I defined, but so continuous and strictly monotone function of psi. So we define like this one. Okay, just defined now. So here is you can find so similar form of similar as operator mean, and also if psi is a logarithm in this case is we can say solidary. So another one is Mosonyi and Ogawa introduced a new Reny entropies, which explained in the morning session by Hiai a little. Okay, this is the new Reny entropy. Why is new means that if A and B is commute, in this case this is alpha power. That's why this is a standard Reny entropy. Okay, so Mosonyi and Ogawa so check this permanence property of F alpha, like so monotonicity and also positivity and also another one, three standard properties. And so you can, so and then I understand that, so how to formulate, so using the operator mean. So maybe you can guess. So here is so new version. Okay, here just replaces this form. So you can so change it easily, so like this one. Okay, this alpha power is so enter into this form and etc. So you can guess new entropy or not, but a new form like similar to entropy. Okay. So my question is, so this is so last slide, and this is my question. Maybe someone maybe can give some comment to me. So it is welcome. So if psi is x alpha power, then it is so as Furuichi so ask, I'd like to know the relation between the f sub alpha and the f psi. Okay, which one is bigger or which one is lower, or there is no relation or not. In any case, it's okay, but I would like to know. Second one is if psi is operator monotone function. In this case, its form is solidary. And then, so how about the lower bound and upper bound? I don't know, so this has meaning or not. But anyway, this is my interest. The last one is check the basic permanence property of these psi and f psi. Okay. This is my now, so try to study. And thanks for your attention.